Here is a question from 2017, and this relates to a realistic scenario where we're given three different frames, one corresponding to a 3D camera, which is going to be able to tell us where things are in 3D space, one relating to the location of an object, a bottle in this case, and one relating to the object of the end effector of a robot. And what we're told is basically that E relates to the location of the end effector. This is the end effector frame. C relates to the camera frame, and B to the bottle frame. And we know various translations. We know CP Borg. So in other words, we know the location of the origin of frame B within the coordinate frame of C, right? That's what we're giving by this. That's what this translation gives us. And we're also told EP Borg. So we're also told the location of the origin of the bottle frame here in the frame of end effector E. We're also given the fact that there are certain frame alignments. Now we can see actually most of them, if not all of them, just by looking at the way that they've been drawn. First thing we note is bottle frame B and end effector frame E aligned pretty well. In fact, they are aligned. And frame C relative to frame B and frame C is slightly different. So what we have to do is bear in mind that it's telling us that XE, right, the direction of axis, the x-axis in E is the same as B. It's telling us that, and it's also the same as negative x in C. So we can actually see that, but it's just pointing out exactly that is the case. And it's also telling us that Z in E, that's the one going up here, is the same as Z in B, and this one in fact is then the same as negative Y in C. So you can actually get that information just looking at the frames, but that's just to confirm it. So now what it's asking us to do as a first question is to derive the homogeneous transformation such that we can represent the bottle frame with respect to the camera frame. So we want the transformation B to C. So mapping frame B, something in frame B, to frame C. And then we've got to use that, and we'll see we actually have to calculate the inverse, as part of the calculation to derive the homogeneous transformation that represents the camera frame with respect to the end effector frame. So in other words, it maps from C to E. And we're given this sort of about route just as an example, really. Okay, so first of all, we note, we write down the two translations that we are aware of. So the origin of the bottle frame in C is given by this coordinate representation, this translation of 0.5, 0.75, 2.6, and the origin of frame B in the frame E, which is given by the end effector frame, is given by the XYZ values 0.4 minus 0.65 minus 0.75. So in order to derive then the homogeneous transformation, which will basically represent the bottle frame in the camera frame, so in other words, to get the transformation B, which takes us to C, first of all we need to line up the axes. So we need to say we see that frame C, and we're doing it basically, we've got to look at C and see how does that relate to B. Well, we see C, x of C, is effectively minus B in terms of direction. We see YC, which is going down, represents minus ZB, so it's changing the sign and it's changing the axes. And ZC, which is coming out this way, is the same direction, well, it's the opposite direction of y of b, right? So y of b. So we need the transformation matrix, which basically maps xc, the max minus b, minus xb maps to xc, minus zb maps to yc, and minus yb maps to zc. So it's relatively easy to work that out. So in other words, xc is got to equal minus yb. So there's got to be if we have this is going to be a 3 by 3 rotation matrix. We only want to pick out the xb term, so we're going to have a minus 1 of that and 0, 0 here. Then if we evaluate that top row by that column there, we see that we end up with the first equation. In the second case, what we see is we want to pick out yc equals minus zb, so it's 0, 0, minus 1. We'll pick out this value and change the sign. And the third line shows us that zc has got to equal minus yb, so we have a 0 there, a 0 there, and we want to put a minus 1 in there to pick out that value there. So that gives us the rotation matrix then between B and C, right? That rotates frame B into C. Now, we know that the structure of the homogeneous equation is always going to be of this form. So the upper 3 by 3 part is a rotation matrix on the left. Then we have a 3 by 1 translation vector. And then at the bottom we have a 0, a 0, a 0, and a 1. So we've already got the rotation component, but we've already given the translation component, right? So we already know how to map the origin of B to C, and we've all been given that transformation. So we just have to plug those values in. This is a 3 by 3 rotation matrix component that we put up the top here. Our translation component goes in here, there, there, and there. And of course, 0, 0, 0, 1 goes along the bottom row because it's a homogeneous transformation matrix. So we've done the first part. Now it's saying use the result from that and other things. It's not saying that that's the only thing we have to do to represent basically camera frame with respect to end effector frame. So in other words, we've got to calculate the homogeneous transformation which maps from C to E. Now, to map from C to E, we need to map from C to B and then B to E, right? So we've already got B to C, but we haven't got C to B, right? But we'll get there in a second. But we're basically breaking up as going via B. So we're going to go C to B and then B to E. And we can multiply those two homogeneous transformations together to get the one that we want. Now, we don't have C to B, right? We haven't got C to B, but we've got B to C. So what we can do is we can take the inverse of the thing that we've just calculated, and that'll get that part of the equation sorted out. And the nice thing about doing inverses with rotation matrix parts anyway is that you can just use the transpose, but we'll come back to that in a second. So basically what we can do then is we can calculate this transformation of E to C to E, right, by multiplying the part from B to E with the inverse of the bit that we've got already from B to C. So now let's concentrate on the first one here, this B to E transformation. Right, well, first of all, what we want to do is we want to represent E in terms of B, and we see that they're both the same, right? They're both E and XE equals XB in direction. We also notice that YE is the same direction as YB, so YE equals YB, and also ZE equals ZB. So we've got we basically have the identity transformation between those coordinate frames in terms of rotation. We also know that we've got a translation, right? We know that how to get from the origin at B into the frame of E, because we've already been given this EP Borg. So this is the representation of the origin of B in the frame of E. So we've now got the two bits we need, right? So we can say, well, we've got to map between them, we don't have to rotate because they're already aligned. So we use the identity matrix, and then we put in the shift, the translation that we've got already, and then we can map basically things in the, well, we map frame B to frame E, points in frame B to frame E. So before we had the translational, the homogeneous transformation B to C, right? If we then, basically we want to get the inverse of this. So we can take out the rotational component, and because it's a rotation matrix, we can just transpose it in order to get the opposite, or the inverse transformation. That's easy to do. So in other words, rows become columns, rows become columns, rows become columns, right? So that was an easy thing to do. And we also know how to generate the overall inverse homogeneous, it should be transformation matrix, because if we want to get the inverse of B to A, what we have to do is we have to take, we want to do we need to break it down into its components. That's one way to do it. You could just actually, you could just do the whole thing and use a matrix inverse command. If you're doing things by hand, then obviously you have to start analysing them in a bit more sensible way like this. So what we can do is we can break it down into the inverse rotation, and then minus the inverse rotation times the translation. Right, so we just basically break it down. It's not just minus the translation, of course, because this thing is not doing things in the opposite order. It's still always doing a rotation and then a translation. So we've done a rotation and translation. If you did the minus translation and then the minus negative rotation, obviously that would also work. But what we're doing is we're doing it in terms of a homogeneous matrix. Therefore, we get this other component coming in to affect the translation we're going to do. So we can basically put in, this is the inverse rotation already. So we're going to have to put the inverse rotation into this component, and then we'll multiply it by the translation we had and change the sign, and then we've got all the parts we need to do the requested inverse, right? So what we do is, first of all, we calculate the translation component. It's going to be the inverse rotation multiplied by what we know is the translation. We have to multiply that out and we get some value. And then basically we stick them together in all those two parts to get our C to B transformation. And in order to actually calculate the final homogeneous transformation matrix we've been asked, it's going to be what we had before multiplied by this new term appropriately, leading to the final result. And this then will represent camera frame with respect to the end effector frame as requested. And that's just an example of the kind of information you get at the back of the exam books normally. Obviously, if you do these things online, then you've got a bit more opportunity to find information.